suppose you have a region of magnetic field, right? And there is, so I'll just draw a separate diagram here. Suppose you have this region where there is a magnetic field. We are not going to bother with how this field was created. Let's just say it's a uniform magnetic field. The symbol for magnetic field is B, just like for electric fields it was E. All right. And let's say that you have a charged particle, positively charged particle, that's moving in this magnetic field in this direction. So the velocity of the instantaneous velocity of the charged particle is in this direction, right? What effect will this magnetic field have on the charged particle? Now, the answer is that the magnetic field will exert a force on this charged particle, and that force is given by this expression. So the force is given by F is equal to Q, which is the charge of the particle, multiplied by V cross B. V is the velocity of the charged particle, and B is the magnetic field that the charged particle is feeling, right? So you can see that it's a lot more complicated than what happens for in the case of an electric field. So for an electric field, just to remind you, and one last time, if you have a charge Q in this direction, what's the force on this charged particle in the electric field? Yes, exactly. So you can see that for the electric field, it's very simple. The force is just Q times E. But for a magnetic field, the force is a lot more complicated. It depends on the velocity, it depends on the magnetic field, it depends on the charge of the particle, and it also depends on the orientation of the velocity and the magnetic field vectors. So let's figure out the direction of the force. So the angle between the magnetic field and the velocity vector is this angle, right? So how do we find the direction of the magnetic field, the force? So you know how to do a cross product, right? So and you probably remember this rule for the cross product. You point the fingers of your right hand along the first vector, curl them towards the second vector, right? So based on that, can somebody tell me what's the direction of the force?
Into the page.
It is into the page, exactly. So if you use that rule, what you would do is you would curl your fingers in the direction of V. Let me see if I can hold up my, oh, I can't hold up the screen. I'll just redraw it in the notebook here. I'm doing V cross B, right? So you can see I've drawn the vector V like this, I've drawn the vector B like this. So if I use this right hand rule, I would take my right hand, point the fingers of my right hand along the first vector, which is V, and then curl them towards the direction of the second vector, which is B. And now you can see that my thumb is pointed into the page. That would give me the direction of the force, right, for a positively charged particle. And if the particle were negatively charged, then the direction of the force would be opposite what it is for a positively charged particle. So if it were an electron, then the force would be out of the page. That makes sense? So that is how you can find the direction of the force. It's just the right-hand rule. But I think there is a different right-hand rule, which is a little, which is slightly better than this one. So you can use in any right-hand rule you want. But here is the right-hand rule, which I think is a little more easier to use than the one that I just showed you, that you learned in Physics 1. And that right-hand rule involves 3 fingers, your index finger, your middle finger, and your thumb. So how do you use that right-hand rule? And let me just stop my share so you can see me a little clearly. All right. So for that right-hand rule, what you do is, the first thing you do is you have your index finger pointing in parallel to your arm, right? So your index finger is never like this. It is always like that. All right. Your middle finger now should make a right angle with your index finger. It does not have to make a right angle. It can also make an acute angle. That's fine too. But let's just keep it as a right angle for now. So your middle finger is making a right angle with your index finger. Remember that your index finger is lined up with your arm, right? Okay. So now your index finger and middle finger define a plane. The third thing that you need to do is your thumb. Your thumb needs to be perpendicular to the plane made by your index finger and your middle finger. Now what you want to do is your index finger should point in the direction of the velocity vector, right? So point your index finger in the direction of the velocity vector in the diagram that I have. Oh, you can't see that diagram. Okay, so I'll just show you over here. So this is the velocity vector and this is the magnetic field vector, right? I have my index finger, middle finger, and thumb all oriented like this. Index finger should point in the direction of the velocity vector. Middle finger should point in the direction of the magnetic field. So as you can see, I'm doing that over here. The thumb, which is perpendicular to both of them, is now pointing into the page. And so that tells me that for a positively charged particle, the magnetic field is into the page. Is that completely clear to all of you? So index finger, middle finger, and thumb, right? Important thing to remember is that the thumb should always be perpendicular to the plane formed by the index and the middle fingers, right? Once you have that set, point your index finger in the direction of the velocity, middle finger in the direction of the magnetic field, and then your thumb will give you the direction of the force. And I must complete that statement. If the particle is positively charged, the force will be out of your thumb, right? The direction in which your thumb is pointing. And if the particle is negatively charged, the force will be into your thumb. Is that completely clear to all of you? So that is how you can use the right-hand rule to calculate the direction of the force. Okay, so the magnetic force on a charged particle moving with velocity v is given by this equation, right? You can write down the magnitude of the force by just writing. I've been sloppy with the notation here. This should be the magnitude of the force. So a vector cannot be equal to a scalar. So the magnitude of the force is qvb sine phi. Phi is the angle between the velocity and the magnetic field vectors. And this is a formula you've seen in physics 1. It's just a formula for the cross product. So F is equal to QVB sine of phi, where phi is the angle between V and F. So in my diagram over here, the magnitude of F is QVB sine theta, right? And from here, you can also see the unit for magnetic fields. The unit of magnetic field will be newtons divided by Q is coulombs, velocity is meters per second. So this is the unit of magnetic field, but it has a name. This combination has a name. It is called a Tesla. So magnetic fields in the SI system are measured in Teslas, where Tesla is newtons divided by coulomb meters per second. That makes sense to all of you? All right. So let me show you a demonstration of this. Oh, what happened to the sound?
Which produces a beam of electrons. The beam is visible due to argon gas in the tube.
So this beam that you see is a beam of electrons. And basically the electrons, you're not really seeing the electrons, as the electrons which are traveling at insanely high speeds, 10 to the power of 6 meters per second, through the tube, they slam into the argon atoms in the tube and excite those atoms to higher energy states. And then those atoms give off visible light. And so you can see the track of the beams, of the electrons as they pass through the tube. Okay.
Electrons here are moving so fast that gravity is negligible. Watch what happens when I bring a magnet near the beam. The beam deflects, which shows that there is a transverse force due to the magnet on the moving electrons. In general, any charged particle that is moving in a magnetic field will experience this fundamental magnetic force. The beam is horizontal.
All right, so is that clear to all of you? So you could clearly see that a magnetic field made those particles deflect by exerting a force on those particles. That clear to all of you? And if you rewatch this video later on, you can see the direction of the magnetic field. It would be coming out of the North Pole, and the North Pole is usually red. It's painted red in a magnet. So you can verify for yourself that the particles did deflect the right way by using the right-hand rule. So I would highly recommend doing that. Okay. Now, there's an interesting practical application of this. Have any of you seen these kinds of tubes, these very, very old computer monitors or TVs? Any of you seen them? Okay, so in the old days, this used to be what a TV would look like. And if you go to some of the really old labs in Vanderbilt, you'll be able to see some relics like this, some computer monitors like this. So the way these work is that you have if this is the screen, there are phosphors on the screen, right? And so when a phosphor is hit by an electron, it starts glowing, right? So the screen has very, very small regions which have phosphors on them. So each square represents a region with a phosphor on it. And so if you hit the square with an electron from behind, that square will glow, right? And so in a black and white TV, which was state-of-the-art technology 70 years ago, you could create an image by lighting up some of these squares and not the others. So you could create a black and white image like that, right? And in color TVs, you could create an image by which was even more advanced technology from the 1960s or so, I think. You could create an image by having more complicated phosphors which would light up with different colors when they were hit with electrons. But the key is to hit each section of the screen with an electron, right? And so in the TVs, like there would be 500, so this would be one line of phosphors. There would be 555 lines, I think, of phosphors, which would cover the entire screen. 535 lines of phosphors, which would cover the entire screen. And so electrons would hit these phosphors one by one and lighting up some of them, not lighting up the others, and so on. And so the electrons would hit all 535 lines, I think 3 times per second. So it would have, the whole process would be really fast. And so and that's called painting the screen. So the electrons would paint the whole screen 3 times a second. And so you would see an image on the screen, and then you'd see the next image. But all of this is happening so fast that it would seem like it's happening smoothly. So it would look like a movie, like a video. So that is how these TVs worked. But the question is, how do you get these electrons to their right places, right? So the way it worked was, you had an arrangement like this. This is called an electron gun. It fires electrons. And so this electron gun would send out these electrons, which would come out of this hole. But then you need some mechanism to guide these electrons to the right place on the screen, right? And so the way you would do that is you would use 2 magnetic fields. So one magnetic field would be like this, and another magnetic field can be like this. So the magnetic field that's horizontal would deflect the electrons in the vertical plane, and the magnetic field that's vertical would deflect the electrons in the horizontal plane. So that way you can deflect the electrons to whichever point on the screen you want, right? And so by varying these magnetic fields, you could deflect each individual electron to where it needs to go on the screen, and that way you could create the picture on the screen. That makes sense to all of you? So that is how TVs and cathode ray tube monitors worked in the very old days. If you have an old TV, what you can do is you can bring a strong magnet near it, and you will see that the image gets completely distorted if you hold a magnet near the TV. And that is because of the earlier demo that I showed you, where the paths, where charged particles get deflected in magnetic fields. So yeah, if you have an old TV, you can try that, and you're not worried about destroying it. Just bring a strong magnet near the screen, and you will see that the picture gets completely distorted. Right?